All right, folks, we're back here for part 2. And we just did problem E, part E for that. And the technique that we used, the new technique, was we took the log of both sides. So again, it's like you can take the square root of both sides. You can divide by the same thing on both sides. You can raise something to an exponent on both sides. We can also take the log as long as it's the same base. In this case, we used base 10. Now in part F, the base here is e. E raised to the x equals 11. Okay, so very similar problem here. It's just the base is different. So we're going to get a different solution to that. Now think about this. Yes, we want to take the logarithm of both sides, but is there an easier log to use than just a base 10? What goes with e? When the base is e, that is where we use the natural log, ln, that's ln. If we take the natural log of e to the x on both sides, we can also do that as long as it's the same base. And remember that ln is the same as log base e. Log base e. It's a short way to write it. Now, using our rule here, when you have a logarithm and then this value raised to an exponent, we can put the exponent out front, and what we get is x times the natural log of e equals the natural log of 11. But we can go even further here because we've already talked about there's a property that if you have, let's say, log base 3 of 3, if the base and this value are the same, then the answer is just 1. The log base e of e, which we write as ln e, wait, that's just going to be 1. So this right here becomes a 1, and so we get x times 1 equals the natural log of 11. X equals the natural log of 11. Okay, so then I can just type that in. So ln 11, and we get, okay, so again, we get this decimal. I'm going to go to 3 places again, 2.39. Now this 7, because the next digit is 5 or higher, I would make that an 8. So 2.398. So you have choice. When you are trying to figure out, okay, I'm going to take a logarithm of both sides, what do I want the base to be? You could pick any base. You could do log base 5. Now the calculators, though, they have log base 10, and they also have the natural log, ln. So I wouldn't pick a different base besides those, but if you're dealing with e, it just makes sense to use the natural log, the log base e. All right, now that takes us to the second part here, which is logarithmic equations. So we want to solve the following equations here. Now, very similar to what we did with exponential, the concept, if the bases are equal, then the exponents have to be equal as well. This is going to be the same concept. If we have the same bases, the log base 3 and the log base 3, if those are the same, then these expressions have to also be the same. So if, I'll write it this way, if the log base b of m is equal to the log base b of n. So if we have the same base, then that means that m has to be equivalent, equal to n. So in part A here, well, log base 3, log base 3. So that means that this and this have to be the same. 2x is equal to 16. Divide by 2, and x is 8. Now, in part B, we don't have that. We don't have a log on the right side. Well, let's remember that a logarithm is just a different way to write an exponential equation or an exponential function. Let's take this and convert it to an exponential equation. So we have the base, which is 4, raised to the exponent. All right, a logarithm is equal to an exponent. That's 3. So 4 raised to the 3 is equal to, and then this expression is 5x plus 9. Now you might be tempted to do some more complicated things, but actually we're not going to take the log of both sides. We're not going to get a common base because the variable is not, it's not part of an exponent, okay? 4 to the third, well, that's 64, equals 5x plus 9. We're just going to solve this like a normal equation. So we'll subtract 9 from both sides and divide by 5, and we get x is equal to 11. All right, now the last one here, ln, and then 3x minus 7 is equal to 4. Remember that ln, the natural log, is the same as the log base e. Let's convert this. Let's change this from logarithmic to exponential. So the base raised to the exponent is equal to 3x minus 7. E is a number, 2.7 something. Okay, so we're going to take e to the fourth. I'm going to calculate that at the end. Let me move the negative 7. So e to the fourth plus 7 is equal to 3 times x. And then we're going to divide by 3. And x is equal to this expression. Now I'm going to take the calculator. And we want, let's see, e to the, whoops, not 10. Let's try that again. E raised to the fourth power plus 7. Now the plus 7 is not part of the exponent. I got to make sure I get to the right of that. Divided by 3. And we have 20.53, and I'll round that 2 up to a 3, 20.533. And there we go. All right, so let's take a look now. We've got 2 more problems here. We've got a word problem. Number 3 says, how long does it take an investment to double in value if it is invested at 10% per annum, so per year, once per year, compounded continuously? Okay, so compound continuously, we have a formula for that. It's the principal times e raised to the r times t for that. Now, something about this problem that you might be looking at and say, wait, we do not have enough information here, because they do tell us the rate is 0.10 or 0.1, 10%, but they don't tell us the original value. They don't tell us what we're starting with here for the principal. So how is it that we're supposed to figure this out? The key is that the investment is going to double. So whatever we start with, whatever P is at the beginning, at the end of this time period, the amount will be twice that. It'll be 2 times P. And what happens is we can divide both sides by P, and what we get is 2 equals e raised to the, now we do know the rate, it's 0.1, it's 0.10 times t. We solved this problem. We actually did this when we were talking about compound interest. But the way that we solved it originally was we had to go to the calculator because we did not know at this point how to solve this kind of equation algebraically. So we did y, the first equation is y equals 2, and the second equation is e to the 0.1 times t, or I'll use x, and then we graphed. And what we were looking for is, where did the 2 functions intersect? Where did the 2 graphs intersect? And I can find that. And the intersection point is where the x value is 6.931 and the y value is 2. Now in this case, we're only solving for the x. That is the amount of time. So 6.931 years, where we say x equals 6.93 years. Now this is what we found in the notes. But now we actually have an easier way of doing this. We have a technique to get rid of this exponent, to move this variable from the exponent. Let's take the log of both sides. Because the base is e, let's use the natural log of both sides. And what happens is we get the natural log of 2. which is just a number. Now here, the natural log of e, we can move the decimal in front of that. So it's 0.1 times t, and then times the natural log of e. But remember, that's just equal to 1. So actually, on the right side, we have no logarithm here. So now it's an algebra problem. 0.1 times t, we will divide by the decimal 0.1. And let's see what happens here. Hopefully we get the same answer. So we've got the natural log of 2 divided by 0.1, and we get 6.93. Same thing. Okay, and actually I don't want to use x because I want to use the variable t for time, and we get the same thing. So we can solve an exponential equation here. We can take the logarithm of both sides. So we're going to do one more here. All right, this is more of a challenge type problem for you. This is something that you would see in a pre-calculus class, for example. Number 4, the half-life of radioactive carbon-14 is 5,730 years. Now, the idea of a half-life is that all objects are made up of carbon, all natural objects. When those objects die, then what happens is that the amount of carbon in them starts to decrease. It starts to decay. And this one element, carbon-14, decays. Half of it would be gone after 5,730 years. So this is how they measure, for example, fossils, is they take a bone that they have and they measure the amount of carbon that is left in that object, because they know that every 5,730 years, half of the carbon is gone. How old is an artifact that contains 12% of its original carbon-14? And I'm going to put a question mark there. Use the formula A equals A sub 0, e raised to the kt. Now you might be thinking, whoa, he's throwing another formula at us, but look at what we used for here, for the compound continuously for the interest. It's actually the same formula. The only thing that changes is that A sub 0 is the variable, the starting amount, instead of principal, because principal is for money. And then instead of R, for the rate, we're using a constant K. Okay, so where A sub 0 is the starting amount, A is the amount after a period of t years, K is what we call the constant of decay. Okay, so in other words, it is kind of like the rate. It's going to be some percentage, some decimal. So let's see here. The question is, how old is an artifact that contains 12% of its original carbon-14? The original amount is the A sub 0. The amount after t years, which is what we don't know, because we want to find out how old it is. So this is the time. That's going to be the missing variable. And we do know that after that time period, there will only be 12% of the original carbon-14. So whatever this number is, the amount on the left side will only be 12% of that. Well, we can write that as 0.12 times A. In the last problem, we did twice times the original amount, 2 times, because we're doubling it. But now it's going to be less because it's decaying, it's going down, and we'll be left with 12% of this, which is 0.12 times A. And this is going to be actually 0.12 times the original starting amount, A sub 0. Now, because those are the same variable, I can divide that out, and we get 0.12 equals e raised to the k times t. We've got a problem, and the problem is we don't know this constant of decay. They don't tell it to us like they told us the 10% interest rate. So before we can figure out the time, we need to figure out the constant of decay. Now, fortunately, they actually give us enough information to do this, because they tell us in the first sentence that the half-life which is 50%, is 5,730 years. So they give us a scenario where we don't know how much we start with, remember, but we do know that we will end up with half of that, that is the half-life, E, raised to the constant of decay, but now we know the time. In this situation, we know exactly half of the carbon will be left after 5,730 years. So let's figure this out. Let's divide out the A sub 0, because it doesn't matter the original amount. These will be the same. We get 0.5 equals E raised to the 5,730 times K. The variable is in the exponent. Let's get it out of there. So because the base is E, let's take the natural log of the left and the right side. So we get the natural log of 0.5 equals the 5,730K. That exponent can come in front, but we don't even need to do that because the natural log of E, remember, is just equal to 1. So it's this times 1, which means that it's just 5,730K. We're going to divide by that. We're solving for K. Now we're definitely going to get a decimal out of this. We get K equals, and I need to make sure I type this correctly, ln 0.5, I need to put the decimal there, divide by 5,730. All right, now we get this number, negative 1.20968094, E negative 4. E negative 4, I'll bring that over here. We do not write that K equals 968,094. That is not E. We write it, that's a base 10. That's times 10 to the negative 4th. This is scientific notation. Now what that means is that we need to move the decimal 4 places to the left. So this number is very, very small. It's actually 1, 2, 3, 4. So it's negative point. There's 3 empty spaces here. I put zeros, 120968,094. That is the constant of decay. That is our constant of decay. But now that we have solved that, we can take that and now go back to our original equation and find the time. 0.12 equals E raised to the 000. I'll just say 12 times T. Okay, I'm going to show you what I'm going to do here. I do not want to round this and then put this into the calculator. I want to put this whole thing in, but as I'm writing it, I don't need to write everything out. Now, how do we solve this? We're going to take the natural log again of both sides because we have a base of E. The natural log of 0.12 equals, this just becomes negative 0.00012 times T. How do we undo multiplication as we divide? I need to make sure I have the right number of zeros here. And what we get is the time. So let me show you the difference here, why this is important. We'll see if this makes a difference, actually. I want to take the natural log of 0.12, 12% left. I want to divide it by this whole thing, the original constant. So I'm going to tell the calculator to put that answer in there. And what we get is 17,527 now this is years, this is time. I'll just raise it to 0.5. Okay, I'll round it to 0.5. So the time is 17,527.5 years. Let's say I did the calculation though, and I rounded it more. So let's say I did ln of 0.12 divided by, and it was negative 0.00012. Does that make a difference? And actually, if you look at the answers, okay, well, they're both 17,000, but this is like 141 more years. That's a huge difference right there in the time period. Okay, so I don't have to type all of this because I can tell the calculator to use my previous answer, but I need to be very careful about my rounding. When I use a rounded number in a future calculation, I want to make sure I use the actual number. And that is the end of the notes.